Differential Equations Weekly Review. I was going to go over some examples. Well, first of all, I was going to draw a distinction between a first-order differential equation written in this conventional form, which can be used to categorize the different types of first-order differential equations, versus this form, which is the differential form. Okay. And then I was going to go over review homogeneous differential equations, but rather in particular how you can take something that's non-homogeneous in this form or in this form, if it's in differential form, and shift it to be homogeneous. We were going to then maybe look at an example of a differential equation which is not homogeneous, but after using the substitution, we can turn it into homogeneous. We were going to review an example of a Bernoulli differential equation, and then we would go into exact differential equations, what those are, how to solve those, and then the complication, of course, is that maybe we have an inexact differential equation, but by using an integrating factor, which we'll define, we can turn it into an exact differential equation. So let us first see what we mean. Okay. So I could try to categorize my differential equations to be like this, where the derivative of y, our unknown function of the independent variable x, is equal to some function of x and y. Okay. So for example, so we have the derivative of y on the left, and we have some function of both the independent variable x and the dependent variable y. But we can very easily rearrange this using algebra. Just cross multiply, and then bring this term to the left. Now the same differential equation is being expressed in differential form. And you should be comfortable going back and forth between the two forms. Okay. So now let's look at a differential equation, and I'll write it both in differential form and in the standard form. So this is going to be an example of shift to homogeneous. Okay, and of course we could also write it as rearranging differential form, so you could see it either way. Okay, the idea is that if we had instead, if we didn't have these two constants here, we would then have an exact differential equation. I'm sorry, we would have a homogeneous differential equation. For example, you can multiply the top and bottom by x, divide top and bottom by x, and you see now that you have a differential equation in the form y prime is equal to not just a function of x and y, but rather a function of the ratio of y over x. That would be homogeneous, where we proceed by lumping y divided by x into a new variable, a new dependent variable. It's dependent on x because y is a function of x. So y divided by x is also a function of x. And then we would proceed from there to turn this into a separable differential equation. So homogeneous differential equation after the substitution gives you a separable differential equation. Okay, but of course this is not what we're dealing with. It's these two constants, these pesky little twos that make this not homogeneous as it stands. But the idea then is to take the let the old x, if you will, take the x that we have in the original differential equation and let it be equal to a new x, but shift it over. Similarly, we're going to take the y and let it equal to a new y that's simply shifted over by some amount. Okay. And now let's try to complete the substitution. So first notice that the differential dy is just dy and dx is dx bar because n and m are some unknown but constants. So the left-hand side then becomes dy bar divided by dx bar. So that would be equal to, on the right-hand side, we simply do a direct substitution for x and then y. So we get 5 times x, which is now x bar plus n, plus 3 times y, which now is y bar plus m, plus that 2. And then the denominator, we get 3 x bar plus n, 2 times y bar plus m plus 2. And the idea is to make this right-hand side homogeneous by making the constant disappear with the correct choice of n and m. So distribute. And the idea is that we want this to be 0 and this to be 0. So that goes away and we'd be left with a homogeneous differential equation in x bar and y bar. Okay. So now we have to solve 2 equations and 2 unknowns. We have to solve for n and m. Okay, so we'll just write this as a, well, I think we'll just use basic linear algebra here, right? So I'm going to write this as a matrix equation. And it looks like this matrix is invertible, its determinant is non-zero, so I can now multiply both sides by the inverse. So 1 divided by the determinant, which is 5 times 2 minus 3 times 3. And then I'm going to, for a 2 by 2 matrix, the inverse is 1 over the determinant. You exchange the diagonal entries, and you change the sign on the off-diagonal entries. So we get -4 and 6, and then 6 and -10. So we solve for n and m, and it looks like the correct substitution is that x is replaced with x bar plus 2, and y becomes y bar minus 4, which would turn our original differential equation here into this simplified, well, this differential equation, which is now homogeneous. Okay. Okay. So we would then, when we see it's homogeneous, after we divide the top and the bottom on the right-hand side by x bar. Okay. So we proceed by, so use v, I suppose. By calling y bar over x bar, we call it a new dependent variable v. To make life easier, let's solve for y bar, and then differentiate both sides with respect to the independent variable x bar. You have to use product rule because both, v is a function of x bar. Okay, so then we complete the substitution. We get dy bar, or the derivative of y bar with respect to x bar, is equal to and on the right hand side we see get a function of v. Okay, and this is separable, so I'll first move over the v to the right, And I'll combine these two terms by finding a common denominator. Let's see how I'm proceeding, if this is working out. Of course. All right. So then we can bring all the V business to the left. And all the X business or X bar business to the right. And now we can integrate. The left-hand side over here is a substitution. Well, yeah, you'd integrate both sides. And this is some function of V, which I can come back and integrate because it's made a typo in my preparation. So I don't feel like integrating this at the moment. So and then we back substitute. V is really Y bar, X bar after you integrate, and then in turn Y bar. So Y was equal to Y bar minus 4. X was X bar plus 2. So solving for Y bar and X bar, we can just directly back substitute. Okay, and then we would have the implied solution. We would have a family of curves that satisfies the differential equation. I'll probably come back and fix that typo. So, all right. So so that was shift to homogeneous. The next example, sometimes, this time, so this would be the example of y equals z to the alpha substitution. Okay. So this is again where we take a differential equation which is not homogeneous, but turn it into one via the substitution. So here's an example. X times y plus 2 dy minus y squared dx. Okay. So it's very similar that if we didn't let me find that. Okay, if we didn't have this constant, then we would get a differential equation which is homogeneous. As you can tell, because of the degree of the terms, like x times y, that's the combined degree, so 1 plus 1. And the degree of this is also 2. Since they're the same, it's homogeneous. But because of this constant, this plus 2, it's not. But let's just suppose somebody suggests that we try replacing y with z to some power. Okay, can we make this homogeneous? Well, let's just see if it works out. We know that if y is equal to z to the alpha, the differential dy would be the derivative here times dz. And then we just do a direct substitution for dy and for y. Okay, so x times y becomes x times z to the alpha plus 2. dy is the differential is equal to alpha z to the alpha minus 1 dz minus y squared, where y squared becomes z to the 2 alpha. So we've completed the substitution. There are no more y's left or dy's. Okay, so let's distribute. And for this to be exact, we want the degree of each term to be the same. So the degree of x times z to the 2 alpha minus 1 is 2 alpha. The degree of the second term, remember that z and x are the variables, so that's some unknown constant right now. So this is just, the degree here is just alpha minus 1. Here, once again, the combined degree is 2 times alpha. So for all the degrees to be equal, we need 2 alpha to equal alpha minus 1, which forces alpha to be minus 1. Okay. So apparently, if alpha is 1 and we do the substitution, let's see, let's substitute for alpha equals negative 1. Okay. So the combined degree is indeed, for each term, is negative 2. So we can proceed by saying let v equal z over x. If you'd like, z is equal to v times x. So that way, dz, the differential, using the product rule, and this, finding the total differential here would be v dx plus x dv. And then we substitute. Okay. Okay. So let's distribute here, FOIL this out, and let's get the dx terms. So we have minus b to the negative 2, x to the negative 2, dx, and then minus, and then 2b to the negative 1, x to the negative 2, dx, and then we have this term as well. And then we have the dv term, so. Okay. And this is separable, so let's maybe leave the dv term on the left, but bring the dx term to the right. So we can bring all of these to the, well, notice that on the right hand side we can factor out a x to the negative 2 power. And we would be left with 1 over v squared plus 2 over v plus 1 over v squared. So let's just double that up. Okay. So we can bring all the x's to the left and all of these to the right. Okay, so now we've separated the variables, we can find the antiderivative of both sides. We get log of the absolute value of v plus 1 on the left. We get minus log absolute value of x plus a constant of integration on the right. Exponentiating in order to get rid of the logs, we get up to a constant. Okay, and then we can get rid of the absolute values because we see v plus 1 would be either plus or minus this arbitrary positive constant, a divided by x, but since a is arbitrary positive constant, plus or minus a is just an arbitrary non-zero constant. So we see v, and then we back substitute. V was really z over x. Just lump that constant along. And z, what is z? Well, we said y is equal to z to the alpha, where alpha was -1. So z is just 1 over y. And that's a solution. Maybe you can multiply both sides by x times y to get something slightly nicer. Okay. And if you'd like, you can even solve for y in this case. So y is 1 over a minus x, where a is an arbitrary constant. Okay, so that was an example of where we took our non-homogeneous differential equation, which was written in differential form this time. And after trying the substitution, where y is replaced with z to some power alpha, we found that if we let alpha equal -1, we got a homogeneous differential equation. Okay. So the next example I want to try is just a quick review of Bernoulli. First order differential equation. And remember that if you have a first order differential equation in this form, and you have y prime and y, otherwise you have functions of x, this is called first order linear differential equation. And we learn procedures for solving such differential equations by finding an integrating factor. So we'll, so we'll get to review that. But with Bernoulli, what happens is that instead of just a function of x on the right-hand side, you have y to some power. You can call it n or alpha, and it doesn't have to be a whole number. So so this is Bernoulli. And the idea is to do a change of variable where we let z equal to y to the power of 1 minus n. And after completing that change of variable, we're going to get a first order linear differential equation. Okay, so let's look at an example as such. And let's just, for simplicity's sake, assume x is greater than 1. So that log is defined for positive x's, and log is positive for when x is greater than 1. Just to keep things simple. So we first try to get it to write in conventional form, where y prime, the coefficient for y prime is just 1. Here it's not, so we're going to divide everything by x times log x. Okay, so if we didn't have this y cubed here, this would be first order linear, and we would then find an integrating factor. But because we do have a y cubed, it's not linear, it's Bernoulli, where the power n is equal to 3. So we're going to try the substitution where z is equal to, did I use z? Yeah, z is equal to y to the power 1 minus n. So z is equal to y to the negative 2. Okay, and then I'm just going to differentiate. So z and y are both functions of the independent variable x, say. So I'll just differentiate both sides with respect to x. You have to use chain rule on the right hand side. Okay, so I have a y prime over here and over here, but I'm missing this factor, like it's not here. So I'm just going to take our differential equation over here and multiply both sides by that missing factor. And if we did things correctly, well, notice first of all that this is exactly z prime. Okay, now y to the negative 3 times y is y to the negative 2, which is exactly z. And on the right hand side, these cancel. You get y to the 0, so you get 1. Okay, so now you see that this is in the form z prime plus some function of x times z is equal to some function of x. So that's first order linear differential equation. And we know that first order differential equation, we find an integrating factor. Which is defined to be e to the power, well, it's defined so that things work out, I guess. It's defined to be e to the integral or antiderivative of px. Okay. I'm going to ignore the constant of integration here. So the integral of 1 over x log x there. We just use a substitution where the new variable, just let's say u is log x. Du is 1 over x dx. So after that substitution, you just get the antiderivative of 1 over u du, which is log of u. Okay. Properties of logs, and you get your integrating factor is u squared, where u is really log x. So the integrating factor is a function of x. We see it's log x quantity squared. Okay. So we're going to take our first order linear differential equation. That's fine. And the job of the integrating factor is to multiply both sides of that differential equation. And by design of the integrating factor, this should, the left-hand side over here is the result of applying the product rule for derivatives to z times the integrating factor. And you can double check that it's indeed the case. It's by design of the integrating factor, so it's exactly what you should expect to happen. Okay. So then we deprime this thing by finding the antiderivative of both sides with respect to x. And on the left, the antiderivative of the derivative is just the thing. And over here, we might have to use integration by parts. So here we use integration by parts. To get, let's see, forget you can't pause these. And we get, here's our constant, we get x log x minus x up to a constant. Now we're going to solve for z by dividing everything by the integrating factor. Including this constant, that can't be forgotten. Where z, recall, remember we defined z to be y to the power 1 minus n, and happen to be 3, so z is equal to 1 over y squared. Okay, and then if you wanted to, you could solve for y or leave it in the simplistic form. This is our general family of solutions to the differential equation, our Bernoulli differential equation. Okay. All right, so that was just a quick review of Bernoulli. So now we're going to get into exact differential equations. So what we want to imagine is that, let's suppose we have some equation in x and y, and it's equal to a constant. Okay. So, and we know that the total differential for that is just the derivative of this function of x and y with respect to x times dx plus the derivative of the function with respect to y times dy. So if you compute the total differential of both sides of this equation, so here I'm motivating exactness, and on the right hand side you get 0. So the idea is that, notice that this is a differential equation in first order differential equation in differential form. It's a differential form. It's equal to 0. So the idea is hopefully we can maybe somehow go backwards, right? So anti-differentiate to recover this equation, which then gives you a curve which satisfies the differential equation. Okay. And assuming this function is sufficiently smooth, imagine you differentiate this with respect to y, but you differentiate this with respect to x. So those are the second order mixed partial derivatives, and if f is sufficiently smooth, they should be equal. Okay. So the idea is that you don't know whether this is true or not, right? But if it is, then you have the chance of recovering the function here. So let's look at a generic first order differential equation like this, where m, I should make it explicit, is a function of x and y, and n is a function of x and y. Then we say that this differential equation is exact if the partial derivative of m with respect to y is the same as the partial derivative of n with respect to x. Okay, and if that happens, then we have a chance of solving our differential equation by anti-differentiating. So here's an example of an exact differential equation. Oh, okay. So this is m. It's the thing that multiplies the differential dx. This is n. It's the function that multiplies the differential dy. Okay, we're going to check whether it's exact or not. So we're going to check whether the partial derivative of m with respect to y is the same as the partial derivative of n with respect to x. So let's differentiate with respect to y. And here differentiate n with respect to x. And indeed we see that these are equal. So we have an exact differential equation. And so now the idea is that we hope to find some function of x and y such that the derivative of that function with respect to x is our m, and the derivative of this unknown function with respect to y is the n. So we're just going to take m and set it equal to the derivative of this unknown function f with respect to x. So maybe I'll write it in a different way. So the idea is that we want to undo this partial derivative of f with respect to x by anti-differentiating with respect to x. So just find the antiderivative. And here we're treating x and y as independent variables. So we find the antiderivative with respect to x, y is treated like a constant. And instead of a constant of integration, you have to include some unknown function of the other variable y. So here we were finding the antiderivative with respect to x. So our function of integration is the function of the other independent variable y. Okay, but we also want to take advantage of this information. So we want to know we want the partial derivative of f with respect to y. Okay, I'm going to write y prime because we have a function of just y, so it's the prime implies a derivative with respect to y, and we set it equal to n. Let's see what n is. All right, so here's n. So and if you look at this equation, both of these terms are on either side of the equality, so they cancel. Then you're left with y prime. Y is equal to 2. So this function is equal to 2 times y up to a constant of integration. And so now we can update f from over here, where f is a function of x and y. Where now we know phi of y is 2y. And then our solution curve would be the equation where our function is equal to some arbitrary constant. Okay. Cool. So to reiterate the procedure here, if you have a differential equation, let's say in this differential form, if the derivative of m with respect to y equals the derivative of n with respect to x, it's an exact differential equation, in which case we can use this method of finding a solution in this form. By first integrating m with respect to x, not forgetting that we get a function of the other variable y as like this constant, quote unquote, of integration. Okay. Then you differentiate this with respect to this result with respect to y, and you set that equal to n, and then this will allow you to solve for phi of y. And once you have that, you know your function and you have a solution. Now the order in which I integrated and then differentiated didn't matter. I could have first integrated n instead with respect to y, and our function of integration, so to speak, would be a function of the other independent variable x. Then I would differentiate that result with respect to x, and I would set that equal to m. That's also doable. Okay. So then there's this idea of, well, What if my differential equation isn't exact? Is there something I could do to make it exact? Well, yeah, sometimes you can multiply your differential equation by an integrating factor, which will turn that inexact differential equation into an exact differential equation. So let's look at a quick example. So here's an example of an inexact differential equation. Okay. Okay. So I see m is the function that multiplies dx. N is the expression that multiplies dy. I'm going to check for exactness. I'm going to differentiate m with respect to y to get 1. I'll differentiate n with respect to x to get 2. 1 does not equal 2. So this is not exact. Okay, but suppose I tell you to multiply both sides of this original differential equation by y. Just like trust me. Just multiply everything by y. So we would get y squared dy plus 2xy plus y squared e to the y dy. So now we have a new m, so to speak, right? The new m is y squared, and the new n, after multiplying both sides by y, is here. And then I'm going to check for exactness again. So the derivative of m with respect to y is 2y. The derivative of n with respect to x is 2y. So now these are equal, and now we have an exact differential equation. Okay. So the idea is that if we have a non-exact differential equation, perhaps we can find something, in general, some function of x and y, which when after multiplying both sides by that integrating factor, that function, we do get something exact. Right? All right. So now let's find a solution to this exact differential equation. Sorry, this is dx. Yeah. So I'm going to recover f by integrating m with respect to x, and we get some additional function of y. Now we differentiate f with respect to the other variable y, and we'll set that equal to n. Okay, so conveniently these cancel out, and this is a good sign if we have that, phi is a function of y. After all the cancellations, we better just have a function of y here for phi prime. So we just have to find phi of y, just find the antiderivative of y squared times e to the y with respect to y. And I guess that's just integration by parts, or really, so I'll quickly use tabular integration by parts. So phi of y is okay. So now we have that our function of x and y, our expression here is y squared times x plus phi of y. So all this extra business. And our solution to the original differential equation then would be this function, the level curve, a level curve for this function. Okay. So next time, we'll look at differential equation written in this differential form, which are not exact. And we're going to talk about finding an integrating factor. So some function which multiplies both sides of the differential equation to force it to be exact. So we call that, let's say we call that integrating factor mu. In general, it's a function of x and y, but we can have special cases where it's just a function of x or just a function of y. It's a function of some combination of x and y, so on. So the job of that integrating factor, and we'll look at ways of finding it. It's not easy because it's not unique. Frankly, I don't even know if it always exists. So you'd multiply both sides of the differential equation by the integrating factor so that it becomes exact. So the differential equation becomes exact. So the derivative of this new m, so to speak, with respect to y will be equal to the derivative of this with respect to x. Okay, so that's going to make it exact. And it's exactly this condition that gives an exact differential equation, which is going to determine how we define mu. So that's next time. Thanks.